the algebraic problem, and the final packing. But the problem is that it's hard to argue that, that the solution will look like we want the solution to look like. The solution could look like completely crazy and in a completely different manner. So this we saw already before, and this is what we have to prevent. And the idea to prevent it is very simple. It's exactly the same thing that we do in jigsaw puzzles, right? In jigsaw puzzles, you know this piece must fit there because there is no other piece fitting there. So what we can do is we can just take part of the boundary and make it similar to a jigsaw puzzle. And then there's one piece which can fit there, one item which can fit there, and it has some wiggle room. And if a different item would come, it would just not fit, because this is how we constructed it. And in this way, we can enforce that everyone is at the location they're supposed to be. And we can also do this between different pieces. And in this way, we can really control how our solution looks like. However, this is not working anymore when our pieces are convex. So we still want our pieces to be at certain positions, but we have not. We want our pieces to be convex. This means that they cannot interlock. Okay, and the way to do it is there are two tricks. So the first one is that the size of the pieces and the size of the container is almost the same. There's only a teeny tiny difference. So this we construct. And then if there is some corner, every corner will have a very specific angle, and there will be only one piece with that specific angle. So this would be the angle here. So if we place that specific piece there, that's fine. But if a different piece would be placed there, this green one here, then there has to be a gap. And this gap will just be larger than the difference between the container and the area of the pieces. And in this way, we can enforce that every piece is at the location it's meant to be. OK, so these were just like some high-level ideas that we used. Questions, anyone? OK, so this was it about packing. So now we solved the packing problem, or at least we made some progress on the packing problem. So Paol and Danja discovered, OK, packing is difficult. Let's take 2 bags. So they just have more bags. And so they discover that there is this offering that you can sleep in a cave during your hiking trip. And of course, Danja says, this is amazing. Let's sleep in the cave. Let's make it an adventure. But Paol is a little bit afraid. So what can they do? Because Danja really wants to go in the cave. She thinks, oh, why don't I take torches with me, and then we can illuminate the cave, and then Paol doesn't have to be afraid of the darkness. OK. So let's say this is the cave. Then you can place a torch here. And the torch will illuminate naturally this point, but not that point. And then that would be the illuminated area of that cave. And these 4 torches would illuminate the entire cave. So far, so good. So now the difficult question is, can you do it with fewer than 4 torches? I see some no. OK, some people have seen this talk already, so they know. Someone who has not seen this talk. Alex, you have some idea? You have also seen this talk before. Anyone have any idea? Who has not seen the talk before? Annalena. OK, so I give a hint. There are these crosses here. So there are 4 crosses, right? Can you see? Can you illuminate 2 crosses at the same time? No? So Okay, so everyone sees this. We cannot illuminate 2 crosses at the same time. So we need at least 1 torch for each cross. Okay, so this is the illuminating cave, the famous illuminating cave problem, which is widely studied. Okay, and does everyone understand what this problem is about, and that we need 4 torches here? And 4 torches are optimal because I just showed you how to illuminate everything with 4 torches. Okay. And then a natural question is, can we place the torches at rational coordinates? Can we? How much precision do we need to place the torches? Right? Ideally, we would say it doesn't really matter where exactly we place them. Or maybe we don't need so much precision to describe a solution. And so, unfortunately, this is not the case. I don't know. Hans has seen this probably to the 3rd time now. I'm sorry. But to those who have not seen it before, so it's not possible to, so we actually need for this problem to have irrational positions of the torches. To see this, this will be the cave, which will be the example. And the way that it works is we have here this niche here and there. And then the only way to see these 2 niches at the same time, there needs to be 1 torch on that green segment. And there needs to be 1 torch on this green segment and 1 torch in this green segment. So if you want to illuminate everything with 3 torches, you need to have 1 on each segment. And then, yeah, so then if you have this pocket here and that pocket, so you already know one of the torches is on this segment. Because of these 2 pockets, you can show that the second torch to illuminate the remainder here and there, must be to the left of the red line. So I guess you can trust me that there's such a red curve which is doing this. And the similar situation is here. So we have 1 torch here, and the other torch must be on the right of this red line. Clear? Okay. And now, coincidentally, this 3rd segment goes exactly through this midpoint. And so, yes, there will be only 1 solution, and it turns out that the intersection of these 2 red curves is in an irrational number. So it may sound like a toy problem, but this problem has a long history. So yeah, I mean, there are more than 1,000 papers on this, and people have tried to find better and better algorithms, but there were no exact algorithms known. And this is the reason why. So anyway, so yeah, this is joint work again with Mikkel and Anna Adamaszek. Okay, so, and we could push this farther, so we could even do this for any algebraic number. You give me an algebraic number. So an algebraic number is a number such that there's a polynomial such that this polynomial evaluates to 0, at the 0 of this polynomial. And then what we can do is we can build a cave with rational coordinates such that one of those torches must have this number as the x-coordinate. So this is, so we essentially can encode any algebraic number into these polygons. Okay, and so we have another result which I want to point out. I think this Hans doesn't know yet, so now something new. Okay, so if you look at these torch placements, right? So then these torch placements, I mean, how would you describe such a placement? You would give 2 numbers, right? You say the x and the y coordinate. And that you do for all of the torches. And if you do it in the right way, then for each torch placement, you actually get 1 vector. You can just describe it in 1 vector. So far, so good? Now, I have cave for which there is not just 1 solution, not just 1, but several. So I can take the union of all of those. And what do I get? A torus. I can also get a sphere or any other shape that you like. Questions? Oh yes, I see. Well, okay. Among all valid solutions, assuming that this is a sketch which is not, this is also not the right polygon. The cave will be extremely complex and have features which are not visible to the human eye, and has also a huge number of variables, of structures. But the principle is that you give me some surface that you like, or some topological space, and I can give you some cave such that if I take the union of all solutions, I get this topological space. Okay, so Paol and Danja are super impressed, but they're also kind of angry. I mean, it's not helping them, right? It's really not helping them. And they're like, okay, all the examples you constructed, they're very brittle. They are not these examples that we see. These are just weirdly constructed examples. So let's try to do something about it, okay? So let's try to actually help them, not just study the problems that they're interested in, but actually try to help them. And for this, I would like to introduce you to the concept of smoothed analysis, which I find is really great because it really bridges the gap between theory and practice very well. Okay, so let me introduce you to this smoothed analysis in a nutshell. And let me go back to 101 of algorithms class, first year. You have an algorithm, and then you have lots of instances that you run the algorithm on, okay? Whatever algorithm you have different instances, you run the algorithm, and then for some times, the algorithm returns a solution really quickly, and sometimes it takes a really long time, okay? You may have also different cost measures, like say, how much space, on memory space you need, or how good the solution is. So here all the instances, here the cost measure. And then what we do usually in theory is we do worst case analysis. We say, this is the worst that can happen, okay? But then people in practice say, nope, never seen. Always goes quickly. And there are lots of different ways to explain this. And the way that smoothed analysis tries to explain it, is that they say, well, you have these worst case instances, but they're really sparse. They're very brittle and they don't really happen a lot. And that is maybe also very, when I heard this, it really reminded me on these instances that we generated, because our instances are also very brittle, and if you move them a little bit, then really something else happens. Okay, so this is this. And I want to point out this is not the same as saying a random instance is behaving, that what happens in practice is the same as random. So maybe I skip the random part. Okay, let's skip the random part. So what happens here is we have structure in our instance in real life, but we have also some part of chaos. Okay, and if we take, for instance, this cave here, then what would be a structural feature of that cave? So here, all the angles are orthogonal, right? So that's not coincidence, that's by design. So if we look at this room, there are all the time orthogonal angles. This is human-made. But then there are some features here which are kind of maybe random. Like what exactly is this width? Would it be different if it would be a little bit more, a little bit less? Does it really matter on what the precise distance is? Okay. Okay. Let me try to define smoothed analysis. It's interpolating between random average case analysis and worst case analysis. Okay, so we would take the maximum over all instances and then integrate over all small perturbations and then see how much time you would take for each instance and integrate over all of those examples. So instead of time, we could also have disk space as a cost measure. Yes, and I want to show that this interpolates between worst case and an average case. So if you perturb really a lot, okay, then it doesn't really matter from which instance you came from. You would have this integral, it would just disappear. If you don't perturb at all, if you perturb a lot, then it doesn't matter which instance you started from, because you would perturb so much that you would not recognize the original instance. And if you don't perturb, then you would just take the maximum, which would be the worst case. Okay. Okay. So this is what we did for this cave problem. We looked at caves and we thought about, okay, so we know they are in the worst case ETR complete, but what happens if we allow some perturbations? And we looked at different ways of perturbing this cave. And then we wanted to see if suddenly, even with small perturbations, if we can guarantee NP membership, or can guarantee that our solution size becomes smaller. And we could do this for these types of perturbations, but we found error in our analysis for these types of perturbations. But for those, we now know that actually these problems become considerably easier. Okay, so this is joint work with Michael Dobbins and Andreas Holmsen, with whom I worked in, what do you guess? Where is this? Who said Japan? Can Japanese people confirm? No, it's not Japan. Korea, very good. Yes. Okay. Anyway, so Paol and Danja are still skeptical. They're like, okay, you have this weird concept, and you say, okay, it's not as difficult as ETR, but I mean, you don't really have an algorithm, right? You don't have something in hand. You just do theory. And so now we try to tackle this as well. So we have this master student, Simon, who is sitting in the audience. And he tries to implement an algorithm so that we can find an solve this problem, this case problem. And we're looking for a master student with Eric Jan van Leuven to solve this disk intersection, disk recognition problem here. It's a very theoretical problem, but it's a very good example to see what we can do. Because it's so easy, methods may work. It's much easier to try out algorithms than on maybe more practical problems. Okay, so I promised Simon I would mention him for 5 seconds. These 5 seconds are over now. Okay, so in the last quarter of an hour, I just want to be very brief here. So the hiking trip of Paol and Danja is over. They took some pictures, and they looked at all the pictures they had taken. And now they want to figure out how many squirrels are on those pictures. But they don't want to count by hand. They want to train a neural network to do the task for them. And it turns out that training neural networks is also complete for this complexity class. But I would need to define this more rigorously, what this means. But for the right definition of training neural networks, it's ER complete. Okay, so let me maybe here summarize. So I also promised that I would talk about my Veni project. And so let me try to summarize what is in common of all of the problems that I presented to you. I think in algorithms generally we have two distinctions. So we either have the possibility that there's a spectrum, a continuum of possible solutions. There's not just one solution or a finite number of solutions, but actually an infinite number of solutions. And sometimes, yeah, we have just a finite number of solutions. These cases are very distinct. So methods that work for one case don't work for the other case. And many problems that we find which are really relevant in practice, we have the situation that, yeah, there's a continuum of solutions. And I want to do two things. The first one is I want to identify when this is actually the case for problems which are of general interest. So like I want to look at very general problems. I don't want to be very specific. And then that's the first step that I want to identify. I want to pinpoint these problems are ETR complete, so they really have this continuous flavor. And the other thing is then I want to try to find new methods to solve them or try them out. OK. Then, so these were the pictures that I used. They were either from the Noun project or Wikimedia Commons, and I thank you for your attention. I don't know. What do you want him to be? You want him to be a meatball? Oh, okay. So a meatball he is.
If I'm looking at ETR, or let's say the art gallery problem specifically, and I ignore let's say that I leave smooth analysis to the side. What are the best possible algorithmic approaches for solving?
Okay, so there exists. So you mean in practice or in theory?
Either way.
Okay, so maybe let's start with theory. So there is one approximation algorithm